Welcome everyone, my name is Péter Babarczi and in this talk I will present our paper Routing on the Shortest Pairs of Disjoint Paths. This is a joint work with Gábor Rétvári, Lajos, Rónyai and János Tapolcai. First, I will summarize you the motivation of our work, and after that I will show the algorithmic background of this problem, which is a Serval-Tarjan algorithm, and will show you some implementations, including our own. After that I will show our simulation results, and finally I will conclude this talk. So first, start with the motivation. So in traditional single pass routing, we have a hop-by-hop destination-based routing, and the routing tables looks like shown in this figure. We have a match action for the destination address, and we have an action to forward it to a given next hop. This next hop is calculated by the minimum cost pass algorithms, for example, Dijkstra algorithm, and luckily this kind of next hops assigned by these algorithms line up into a shortest path tree, so it has a simple implementation. We argue that although this solution is optimal for static scenarios, if we have environmental changes, failures, or requirement or fluctuating traffic changes, we need to adapt the network to these changes. So this solution has no load balancing capabilities, and also we need some kind of reaction after a failure occurs. So we argue that instantaneous reaction is required. However, the current solutions are in the control plane, like in the intra-domain routing algorithm OSPF, are not sufficient to do this, because they recompute the whole routing tables, and during this transient phase, some kind of unpredictable behavior is not acceptable for mission-critical applications. Also, in terabyte per second speeds, we do not allow to rewrite packets or rewrite routing tables, so we do not able to use dynamic memory. So our second argument is we are not allowed to use dynamic solutions. We need pre-computed static solutions in the data plane. So these pre-computed solutions consists of pre-installed alternative paths to the destination node, and also we need some kind of tagging mechanism or some kind of mechanism to address these paths and implement the routing for these. In this example from the first slide, we see the shortest path tree with the backlinks, and also in this case we have some kind of secondary or non-shortest path links assigned to each node with these red, green, and blue links, and also we have some kind of tag value assigned to these links. The routing now, for example, will look as follows. If we start a packet from a node v6 with a tag value of 0, 1, we have the match action, which now, besides the destination node, also will match on the tag. With 0, 1 tag, we will match the first rule, the high priority rule in this routing table, and forward the packet to node v1, and at node v1, we receive a packet with a tag value of 0, 1. We won't match the first rule, we only match the second rule, which is forward the packet to the shortest path tree link, which is in this case towards destination D. Our contribution in this paper that this kind of behavior, this kind of routing can be implemented only to forwarding table entries and using only short tag values in practice. So how can we achieve this result? For this, I will show you the very high-level view of the Serval-Tarjan algorithm, which forms the basic idea of our method. So first, the Serval-Tarjan algorithm is a polynomial time algorithm to calculate the shortest pairs of disjoint paths. First, it uses the Dijkstra's algorithm to calculate the shortest path tree. This will give us the shortest path tree next hop, which is denoted by T. And after an edge length transformation, it labels the node somehow with triplets. So without going into the details, these triplets consist of three values. The distance in this modified graph, in the graph with the modified edge lengths shown in this figure, the cost of the disjoint shortest path, disjoint pair of shortest paths, also a PV node which denotes the link, the non-shortest path next hop, and also a Q node, which has a very special meaning in this algorithm. So how we can use these triplets to calculate, to construct the shortest pairs of disjoint paths? So first, the algorithm says we should use the P link of the given node. For example, this shortest pairs of disjoint paths from node F starts on the PV link, which is says its node towards node C, and after that we use some shortest path tree links until node Q is reached. In this case, node Q is the source node, so we do not have anything else to do. The one for the first pass will be this FCAS pass. On the second pass, we start on the shortest pass link of node F, going towards until the node Q of node F, which is D in this case. And after, or we can use also additional T links if there are some shortest pass tree links in this in other cases. But in this case, the Q is already equals to this secondary link. So this only contains the P link in this case. And if we haven't reached the source node yet, then we go to step 1 and replace from node D, which means now we will use the secondary link, the non-shortest pass link until towards the node P, and we go along the T links until the Q link, the Q node, which is in this case the source node. So we have constructed the second pass. So why this algorithm is so useful? So first, if you apply this, there is no link state routing protocol update is required, because it uses exactly the same data which Dijkstra's algorithm uses, and also it runs in order in the same computational complexity. Second, it not only assigns the primary links, the shortest pass links, but also assigns the non-shortest pass links, which we can use for routing in this case. However, it has a very complicated distributed implementation in networks, because now the routing might not be sufficient to use only the destination address. The next hop might depend also on the source node, so we might have quadratic size routing tables, which is not acceptable. And a possible implementation to avoid this problem is to add this kind of dynamic memory I mentioned previously in the talk to the packets and rewrite the packet header. This Auger-Rutenburg-Shaham implementation uses the node, this IDQ adds the packet header, and the match in the bottom of this slide works as follows. We check at forwarding whether the ID in the packet header is the same as our ID as the node. If yes, then we rewrite the Q value in the packet to our own Q and forward it to our non-shortest pass link. And if we are not the Q node of the source of the packet, then we will forward it on the shortest pass link. But as I mentioned, this dynamic behavior is not acceptable for fast reaction. The second implementation, or second possible implementation of the Serval-Tarjan algorithm is the red-blue trees, in which case we have a very fast heuristic to arrange these T and P links into two trees, the red tree and the blue tree, which has the property that starting from any node, for example, if we pick V3, then the blue pass will be completely linked disjoint from the red pass. So this is very simple, because we can have fast algorithms and only a single tag to determine whether we should use the red or the blue tree is required. But it is very complex. It's proved to be NP complete, and also the pass stretch has no upper bound, which could be really bad in theory, but it's quite good in practice. So how can we avoid, or how can we give an efficient solution to route on these shortest pairs of disjoint paths? So we showed that that it is possible to implement such routing with only two forwarding table entries, and this is based. So this is based on the observation that based on the two backward traversals we have seen in the Serval-Tarjan algorithm, these paths will consist of segments. So after because if we use this backward traversal, after we use the P link, after that we go to the Q of this link, and regardless from where the packet started. So in this case, we can decompose the whole path into these segments, and we do not have to care where the packet came from. So we call these SPDP segments, this construction, and an example is shown in this figure. So on the left-hand side, we show a network again, where the black links are the shortest path tree links, and the colored links, the red, the green, and the blue links, are the non-shortest path links. And on the right side, we can see these SPDP segments. The purple ones are the starting on the P links, on the non-shortest path links. So in this here we can see, so the purple one starting on the PV link traverses some shortest path links if there are zero or multiple ones, until the Q node of this P link is reached. The other segment starting from a node, in this case, in this uppercase, from node A9, is the orange one, which starts on the shortest path links and goes until the Q node of this node A9. So these are the two segments starting from each node. So these upper two are from node A9. So these two are from node A2. This is from node V6, and this is from node V4. How can we construct paths from these segments? So each we have shown that because of this Serval-Tangent backward traversals, these two each SPDP path will consist of the concatenation of these segments. For example, the first path on from node A9 will start on this orange one, and after that it will traverse a P link, some T links, and again a P link. So after the first initial orange one, it will only traverse the purple segments. The other paths will consist only of purple segments traversing a P link, some T links if possible, and also a P link and other T links, other shortest path links, until the destination is reached. So now our task is to address these paths. So now we have the structure, the data structure of SPDP segments. Now our task is to find an efficient solution to route the packets on this path, and also forwarding table entries, how to forward these packets along this path. So a naive implementation has the text size of in the order of the nodes, but our goal is to make it as small as possible. So for this, we do a path make a path conflict graph, which looks as follows. So here are three paths in the previous example, starting from node A9, A8, and A7. So we observe that at node A6, which is this node here, the first path want to use the secondary link, which is this green link to node V5, and the other two want to use the shortest path link, which is A5, which is this link here. And also we observe that the paths from A8 and A9 at node A4 are forwarding the packet on the different links. The one want to use the secondary link, which is the green link, and the other want to use the shortest path link towards A3. So these paths are in conflict because at certain nodes they want to use different outgoing links, so they need to be assigned different tag values in a proper forwarding mechanism. So we transform this problem to a graph where to an auxiliary graph where each node corresponds to a path in the original graph, and each two paths or two nodes in this auxiliary graph are connected if they are in conflict with each other. Now we transform the original problem, so the tag assignment in our original graph, to an auxiliary graph, to a graph coloring problem. And now in the second theorem showed that the coloring, the chromatic number of this graph, gives a lower bound to the number of bits or the tag lengths in our tag implementation. Also, this is not so simple. So we won't be assigned these tags arbitrarily to the nodes. So we need some kind of additional constraints. We need to take into account some additional constraints. For example, in the previous example, at the last link from the V4 to D, each path should forward the packet. So although they are in conflict and we should be assigned with different tag values, they also should be able to cover them with a single forwarding table rule. So in this case, we need some wildcard rules. How can we construct these wildcard rules? A very high-level view of our algorithm in the paper is that based on this graph coloring we have previously, we built a so-called SPDP segment hierarchy tree, and we check whether there is a node which has child nodes with different colors. In this case, we have three different colors going to V4, which means that the forwarding table rule or the match rule in the forwarding table should match all tag values assigned to these three paths, which is shown in this case in this right-hand side forwarding table. So our match action will be for this example graph that if the tag value starts with 1 and we don't, the second and the third bit could be 0 or 1, we don't care, and the destination is D, then forward to node D, towards node D, which is this means, sorry, this in this V4 link means this lower non-shortest path tree link towards destination D. And if the packet's not starting with 1, we use the shortest path tree link, which is from V4 will be V3. Also, if the node, for example, A6 has child nodes only with a single color, then exact match will be sufficient. Okay, so this is how we address these shortest pairs of disjoint paths. So now I will show you our simulation results. So our first observation was that we ran several simulations on real-world networks and also on synthetic topologies, that although we do not have a bound on the upper bound on the length, in practice, it's sufficient to have only a short length. So in specific, in our simulations, 4-bit length tag values were always sufficient to address these SPDP paths. Also, our observation was that in real-world topologies, only 3% of the match rules for the non-shortest path tree links is wildcard rules, which is a good sign because it's not fully compatible with current traditional routing methods. Our second observation or our second simulation was to compare this method to path splicing, which is an implementation for source selectable routing, where we have 2 or 5 routing trees in this simulation, where these routing trees are a bit different from each other, and the packet can switch the trees at each hop and will reach the destination on different paths. So our implementation compared to this method is able to provide alternative paths to each source node, while path splicing, we can see from the figure, 10% and 30% of the node pairs do not have an option to avoid faulty link or a congested link in this case. So our solution provides 100% alternative paths for each node, and also we provide to about 85% of the nodes 3, 4, or even multiple paths to choose from if it's not a problem that this path length will be longer than the shortest pairs of disjoint paths. And finally, our third investigation was, can we use a different implementation than tags to address the SPDP paths or SPDP segments? And segment routing is a quite straightforward solution because we have a quite good correspondence between the segment routing segments and our segments in the SPDP segments in our Serval-Tarjan results, because each SPDP segment consists of at most adjacency and the shortest path label, or only the one of them. So this we can calculate an upper bound on the segment routing implementation. And our observation is that although we were able to improve the previous solutions, reduce the label stack size in the segment routing implementation, the current routers only support the depths of 3 labels. So it's currently it's still not a viable option, but in the future, if the routers will evolve, then also a segment routing implementation will be good to address these SPDP segments. To summarize this talk, we provided the first efficient data plane encoding for the shortest pairs of disjoint paths, which is backward compatible with traditional link state routing. We do not need to change the message exchange between the routers. It is incrementally deployable for a subset of routers to have partial gains to provide alternative paths for subset of nodes. Also, our SPDP segment data structure provides optimal data plane scalability with only 2 forwarding table entries. And finally, our proposed tagging mechanism ensures negligible packet overhead. So in practice, we only had 4-bit tags. So thank you very much for your attention. Bye.